all of you. So, theory, we have seen in last class, right? So, what we have seen? That we have seen the continuity equation, right or not? So, in order to analyze any semiconductor, right, we need some basic equations, right? So, first is there are transport equation for both electrons and holes, and another is called continuity equation for both electron and hole. Okay. Also, we have seen what is a Gauss law, right? Gauss law, you understood, na?
Right, sir. Right. Understood.
This is Gauss law, right? So, the change of electric field with respect to d by dx is equal to the volume charge density by epsilon, right? This is what we have discussed last time. Okay.
Einstein's equation.
Pardon me.
Einstein's equation.
Yeah, not audible. Can you tell me?
Einstein's equation.
Einstein's equations you have studied in the transport chapter, right? So this is called Gauss law, right? The increase in electric field, okay, increase in electric field D, okay, is nothing but depend upon the how much charge that is enclosed in the volume. I don't know.
Right. Right.
Yeah. So dE by dx is equal to the derivative of electric field with respect to distance. dE by dx is equal to the volume charge density by epsilon. Okay, this is what we have discussed. Also, we were trying to derive a compact representation of the transport equation. Clear? So there we have discussed, we know the concentration of electron nothing but Nc exponential of minus Ec by Ec minus EFn by kT. Okay. Then if you do the derivative, right, we will get this equation. And this equation one was clear to you last class. We have just taken the derivative.
Yes. Yes.
Okay. So, and this is nothing but my depth equation, where the electric field is nothing but 1 by q. So we know EC representing the potential energy, right? So derivative of potential is nothing but electric field, right? So derivative of potential energy by q is the potential, and derivative potential is nothing but electric field. Clear?
Wait.
EC is the potential energy. Potential energy divided by q. Okay, is nothing but my potential. Potential derivative of is electric field. So this total is giving my electric field. Okay. So if you sum both equation 1 and equation 2, so this q get cancelled, right? So what is my Jn? Jn is nothing but q dn by dx, which is nothing but my equation 1, right? Q n mu n e is nothing but my equation 2. I don't know.
Right.
Right. So if I add this two, this is my transport of due to diffusion. This is due to drift. If I add these two, right, this EC thing will get cancelled. Na? See, n mu n minus dh by dx will get cancelled with n mu n dh by dx. Right?
Right.
What I'm telling, equation 1 have to be added with equation 2 to get Jn. Right? Equation 1 is diffusion equation. Equation 2 is drift equation. If we add drift by diffusion, I will get the total current.
Right.
So if you add this n mu n dh by dx will get cancelled with n mu n dh by dx. So I don't know. So what we have is the total current Jn equal to n mu n EFN by dx. Right? From the equation you see. If you add this equation 1 with the equation 2, what you will get? N mu n dEFN by dx. Right or not? Hello?
Yes, sir. Yes, sir.
Yeah. So what is the summary of this equation is the gradient of my Fermi level, okay, gives the information about the current. Right? If current is 0, then the gradient of the Fermi level should be 0. Okay. So note is what? Note is the gradient of Fermi level contains information of about the drift as well as is this clear?
Yes, sir.
Okay, so whenever there will be a gradient in the Fermi level in the energy band diagram, you understand that there is definitely some current flowing through the device. Okay, fine. Hello,
So, sir,
is this fine?
what's the last thing you said?
Last thing I'm telling you, whenever there is a gradient in the Fermi level, definitely there is a current in
Change
the
in
device.
current. Yes, yes.
Then the Fermi level is constant throughout the device, that is in equilibrium, right? So we have seen the equilibrium, the Fermi level is constant throughout the device, then the current is zero.
Okay.
Okay, so one more thing which is not needed for the exam. So the continuity equation, right, will be simplified in for different conditions. Suppose if you tell equilibrium means dn by dt is equal to 0,
Okay.
right? Jn will be equal to 0. So like if you so I'm telling for different conditions, this continuity equation will be very simplified. Okay, so this condition we need not to see now, because for example if you go to the if you go to equilibrium, in equilibrium what is that? Jn equal to 0. Suppose I will tell, suppose in equilibrium, suppose suppose I am in equilibrium. Okay, equilibrium means what? Jn equal to 0, Jp is equal to 0. I don't know.
Fine.
Right. Jn equal to 0 means what? Dfn equal to 0. Jp is equal to 0 means dfp by d equal to 0. Okay, that's what the meaning of this. The Fermi level for the electron, the Fermi level for this is nothing but quasi Fermi level, right? Okay, quasi Fermi level is for electron. This is the quasi Fermi level for holes. Okay, so in equilibrium, current equal to 0, and the Fermi level is constant throughout the device. So for different conditions, we'll get different. Suppose this is for equilibrium, right? In equilibrium, what I got is the Fermi level is constant, right or not?
Right.
Because Fermi level is constant, so the current is also 0. The current is nothing but my gradient of my Fermi level. Since at equilibrium the gradient equal to 0, so at equilibrium the Fermi level is constant throughout the device. Clear?
Clear, clear.
Okay. So suppose there is something called suppose a device in steady state. Okay, so suppose there is in steady state. Okay, what do you mean by steady state? Suppose a device in steady state, we know del n by del t is equal to what is the equation? Huh? 1 by q plus generation minus recombination, right? Right or not?
Right.
Suppose in steady state, so what is del p by del t equal to minus 1 by q into djp by dx plus g minus p by tau. Okay, suppose in steady state this is equal to 0, because steady state means what? Everything is constant with respect to time.
Okay.
This is also equal to 0. So if both are equal to 0, right? If you, this is equation 1. Okay, and equation 1, this is equation 2. Okay, so since this is equal to 0, right? And also we know in steady state, if you do 1 minus 2, okay, what it will be? It will be d of jn plus jp by dx equal to 0, right? So what is the meaning of this? In steady state, right, the current is constant through the device, right or not?
Right, sir. Right, sir.
So even though Jn and Jp will vary with distance, if you add Jn and Jp, if it is in steady state, the total current is constant through the device, if it is in steady state. So by putting different conditions in the continuity equation, I'll get different situation, right or not?
Right.
Okay. So with this is just an introduction. We'll start diode. Okay.
Okay.
Okay. My screen visible?
Yes, sir.
Just a minute. So, you know, in exam, right? Suppose in IES conventional exam, right? So based on the continuity question, many questions will come. Okay. They'll give some situation. Okay. You have to put that situation, then you have to derive the concentration or current or something. Okay. It is a complex equation, but different conditions, the equation become very simple. Clear?
Okay.
Just wait, not responding. So we'll start this injection diode. So first we will discuss about basics of diode. Okay.
Okay.
Let it get open. Okay. So what in this PN junction diode, right, is a very fresh device, right? So what we will discuss first. Okay. So this is a very important topic. Okay. So if you understand the device of diode very clearly, right, this analysis or this understanding will be useful for understanding any complex device. Okay. So it's like, you know, in control system, you study the second order equation. Okay. But in reality, almost none of the system is second order. But thing is, if you understand the second order system, you can analyze any higher order system. Right? That is why you study so much concentrating on second order system. Clear? Similarly, diode will be used everywhere. Okay. Whichever device you use, its analysis, its physics will be used everywhere. Clear? So that's why the understanding of the diode is very important. Clear?
Okay.
So we'll first see what is the ideal diode, right? So what do you expect from an ideal diode? Okay. Then we will cover basics of semiconductor physics. Okay. So in that we'll study the PN junction in equilibrium. Okay. Also in non-equilibrium means when it is forward bias and reverse bias. Okay. Forward and reverse bias. Okay. So in both the cases, we'll first study the physics of the diode when in equilibrium. Okay. Then we will disturb the equilibrium. Then we will see in forward bias what is happening and in reverse bias what is happening. Okay. So at the end, we will see the small signal equivalent of the diode. Okay. Meaning it's so diode is biased for a particular voltage and current. Then if you change little bit to the voltage or current, how the respective voltage or current will change. Okay. So for example, if I have a diode, right, I am applying a DC bias. Okay, and this is a voltage, this is a current I. So if you change a little bit voltage on the DC bias, suppose you apply a simple AC on this DC, then the current also will change. Okay, so if you apply a small change in voltage, how much change in current will flow? That will be discussed in the small signal equivalent of the diode. Okay.
Okay.
Okay. So you know, ideally a diode have two terminal. One is a anode, another is called cathode. Okay. So generally it have two bias, two modes. One is called forward bias. Okay. So in forward bias, what will happen? in forward bias, the current to the device should be greater than 0. Okay, when the current is greater than 0, the voltage in the diode will be equal to 0. This is the condition of forward bias. Okay, in reverse bias, so since VD is equal to 0, it behaves like a short circuit. Okay, hello,
Sir, yes, sir.
clear na? Getting what is forward bias? Forward bias means the current through diode should be greater than 0. When the current is greater than 0, it behaves like a short circuit. Okay,
Yes, sir.
similarly, in reverse bias, the voltage across the diode, right, VD, is less than 0. Okay, then the current through the diode will be equal to 0. It means since current equal to 0, it behaves like a open circuit. Clear?
Clear.
So if you want to express in terms of the IV characteristic of a diode, right? So if the current flowing through the diode is greater than 0, the voltage across the diode VD equal to 0. Okay, so this is the forward bias curve. Similarly, when voltage across the diode is negative or reverse bias, in that case the current equal to 0. So it is nothing but my reverse bias. Clear?
Clear.
Clear. So ideally, I want my diode, the IV characteristic, the current voltage characteristic of the diode to be like this. So it will be useful in many varieties of application, most importantly rectifiers. Okay, so ideally people want a characteristic like this. Okay, so in the aim of getting a characteristic like this, people went and discovered PN junction. Okay, then we will study what is a PN junction and how it behaves like a rectifier. Okay, so before getting into PN junction, we'll first understand. I also discuss very clearly what is the entire semiconductor. I'm just giving a recap. Okay, you know, in entire semiconductor, right? Whenever silicon is doped with pentavalent impurity, I get entire semiconductor, right? So in entire semiconductor, we know each donor atom is denoting one electron, okay, and becoming positively charged. So if I want to represent pictorially the entire semiconductor, what it will have? It will have lot of positively charged bounded atom, which is nothing but the donor atoms. This is donors, right? Here, and they are electrons which is donated by the donors, right? And they have very small amount of hole. I don't know.
Right.
This is already discussed, right? A entire semiconductor is formed when a intrinsic semiconductor is doped with donor impurity, right? So if you see the pictorial representation, it have a lot of positively charged bounded atom. These are donors and many electrons that is donated by the donor impurity. Clear?
Clear.
Okay. So it's just a simple example. Suppose ND is equal to 10 power 16% centimeter cube. Okay. Then the concentration of electron will be approximately equal to 10 power 16 per centimeter cube. And the hole will be Ni square by N. Okay. This whole. Okay. So it will be approximately equal to 10 power of 4 per centimeter cube. Clear?
Clear. Clear.
Okay. This is nothing but a simple example I am giving. If I dope with 10 power 16 number of atoms per centimeter cube, then the electron concentration will be equal to the donor concentration and the whole concentration will be Ni square by N will be equal to 10 power 4. Okay. So the whole are very less compared to the electron. Okay. Similarly in a p-type semiconductor, it is formed when a intrinsic silicon is doped with boron impurity or class 3 impurity, right? So it will give one hole to the valence band. Okay, so in a p-type semiconductor, I have many negatively charged bounded atom. They are nothing but my acceptor impurity, right?
Right.
Okay, they are nothing but acceptor. Okay, acceptors. and whenever they donate one hole, right, holes, they become negatively charged, right? So in summary, a p-type semiconductor is formed when it is doped, when a silicon is doped with acceptor impurity, and it have all the negatively charged bounded atom, and the holes, there are very few electrons. Clear?
So why is this negative acceptor atoms? I mean that representation shown big and the others are like small, plus and
Yeah,
minus.
because this is a very big atom, right? It is very big atom. Okay, very big atom. When just giving one hole is very small, right?
Okay, okay, okay.
This is atom. This is atom which is negatively charged. Whenever a atom is accepting an electron, it gives one hole and it becomes negatively charged.
Okay, okay.
These are the atoms which are bounded atoms. These are the free holes. Okay.
Okay, okay.
This is summary of my page. Already I have discussed. Okay.
Yes, yes.
As an example, I am just keeping. So then, what is a p-n junction? So the symbol of a diode is nothing but P and N. It is symbol of my diode that you know. Okay. And a p-n junction is formed whenever you take a p-type semiconductor and n-type semiconductor and make a junction. Okay. So a p-n junction is formed when a p-type semiconductor and n-type semiconductor make a junction. I don't know. It is just a p-n junction. Okay.
Right.
So when you make a p-n junction, so similarly you see this p-type semiconductor is nothing but which I have explained you. Okay. We have formed by putting receptor atom. Okay. The n-type semiconductor is nothing but formed when a intrinsic silicon is doped with donor impurity. Okay. Just for example, I have taken same number of donor and acceptor impurities. Okay.
Okay, okay.
Then we will see what will happen whenever a p-type semiconductor forms a contact with a n-type semiconductor. What will happen? Okay. So this is nothing but in equilibrium. Okay. We could see whenever a p-type semiconductor made a junction with the n-type semiconductor. Okay, what will happen? You tell, since in p-type, p side, there are many number of holes, right or not?
Right, sir.
So naturally, and in n side there are very few holes. Okay, so definitely the holes are very more here, right? So if I
Right.
want to stress in your pointer, okay, can you see my pointing?
Yeah.
Right, you can see
Right.
now.
Yes,
Okay,
yes.
okay. So you see in this region, my holes are very more, right? Here the holes are very less. Similarly, in this region, the electrons are very more, and here the electrons are very less. Okay, so naturally, the holes will try to move from p side to n side because of a concentration gradient, right or not?
Right, sir.
Similarly, the electron will try to move from n side to p side, leaving behind the bounded positive atom. Okay, see how it will happen. So this hole will go from n side to p side, and it will maybe meet some electron and will recombine. Finally, the electron will try to go from n side to p side, p type, and it may meet with the holes and will recombine. Okay, so this process will continue. Okay, so what will happen? You see, in the junction, right, we will have net positive charge, and in the p side we have a net negative charge. Okay, they are nothing but my bounded atoms. I don't know. These are the bounded atoms. These are the bounded atom. Okay, this is bounded donor impurities. This is bounded acceptor impurity. Okay, which are negatively charged. So at the junction we have got net positive charge in n side, net negative charge in p side. I don't know.
Right, sir.
Right. So we'll generate an electric field. Okay, because whenever charge positively charge and negative charge, we will get a electric field. I don't know.
Right, sir.
So what we'll do, the electric field is like this, right? Like this direction. Okay. So the electric field will try to oppose the further flow of carriers. I don't know.
Right.
Because the electric field is like this. So it will oppose the motion of a hole from p side to n side. Similarly, the electric field will oppose the motion of electron from n side to p side. Okay.
Clear.
Clear. But since initially the electric field is less compared to the diffusion force. Okay. So again, there will be further flow of motion. Okay. Like this. Because electric field is weak now. Okay. Again, what will happen? You see, when the further flow, right, the amount of charges in the p side and n side increases. So what will happen? The electric field will increase. Okay, and the electric field will go on increasing, right? Then equilibrium point will reach when the force due to the electric field will be exactly equal to the concentration gradient force. Then whenever we'll set electric field which is exactly opposing the concentration gradient force, then after that there will not be any motion of holes from p side to n side and electron from n side to p side. Okay, the electric field will go on increasing at a particular electric field called built-in electric field. There won't be any further motion of holes and electrons. Clear?
Clear.
Because the electric field go on increasing. So the opposing force for the diffusion will go on increasing. Then whenever the opposing force due to diffusion will be equal to the electric field force, it also I can say drift force, then there won't be any movement of carrier. Okay?
Right.
Right. So what will happen? Then at equilibrium, there is no net flow of carrier across the junction because the electric field created is opposing the further motion of carrier from one side to another side. I don't know.
Right.
Right. So at equilibrium, what we have at the junction, right? We have an electric field and the area near to junction it will be having very less number of electrons and holes. Okay, almost free of electrons and holes. That's why it's called space charge region or depletion region. Okay, right? The area near to the junction, right? This area, okay, is almost devoid of free holes and carriers and electrons. That's why it's called space charge region or depletion region. Okay, here. So because there is electric field, okay, there is a built-in potential. Okay, you see the integration of electric field is what? Called potential, na? Hello.
Yes, sir. Yes.
So since there is a electric field, there is a potential. Hello. Right and
Sir,
right or wrong?
is the potential moving linearly, like in negative potential gradient is electric field?
No. See, that I will discuss. It is a parabolic curve. Okay, it's a parabola.
Okay, okay.
That we will discuss how it come. Okay.
The decreasing nature, I
No,
understood.
because here electric field is maximum. Okay, if you go on here, electric field is minimum. Here see, it is positive, it is negative. Okay, so this is potential. It is positive, it is negative. Okay, after that it is zero.
Okay.
Because here it will create a potential where it is positive. So it is positive here.
Yes, sir. I understood that. Just had that doubt on that curve only. That's
Curve
it.
is a parabolic curve. How it come, we will discuss. Okay.
Sure, sure.
Okay. So we'll discuss now mathematically how all the things is coming. Okay.
Okay, okay.
So in the summary, at equilibrium near the junction, we have a electric field. Okay. It is called built-in electric field. Okay. This is a field which is created inside by not applying from outside. Right. This electric field is creating the opposing force so that there won't be any further motion of carrier. Hello, Surajit. Hello. Surajit. Okay. So this electric field is causing the here the electric field is opposing the further motion of carrier. Okay. That's why there is a equilibrium. Okay. At equilibrium, the electric field force nothing but my drift force equal to diffusion force. Clear? Surajit, are you there? Surajit?
Yes, sir.
Yeah. So we had started the diode. Okay. So
Yes, sir.
yeah, just let me give you a brief understanding of this one. I think you might have know this. Okay. So you know in a pin junction, right? Since there are more number of holes in P side, there are more number of electrons in N side. When you make a junction, right? holes will try to diffuse from p side to n side, right? Like this. Then electron will try to move from n side to p side like this. So there will be a net charge at the junction. So there will be net electric field. Okay. Initially the electric field will oppose the flow of carrier, right? So, but initially the electric field force is little lesser compared to the diffusion force. So there will be further diffusion. Okay. So further diffusion. So again, what will happen? The electric field will increase. The process will keep continuing until the force due to the electric field will exactly cancel the diffusion force. Okay. At that point, we will reach equilibrium. Okay. At equilibrium, there is no net motion of carrier across the junction. That's what I told him. Clear?
Okay, sir.
Okay. So this is my equilibrium picture. At equilibrium, near the junction, I will have almost no carrier or very few carrier. That's why it's called space or depletion region. Okay, because it is depleted of free carrier. Okay, and since we have a positive charge and negative charge here, there is electric field. It's called built-in electric field. Okay, and whatever because of built-in electric field, there is a built-in potential. Okay, this potential is nothing but it is opposing the further motion of carrier. So at equilibrium, drift force equal to diffusion force. Drift force means the force due to the built-in electric field equal to the diffusion force. Clear to both of you?
Clear.
Okay.
Yes.
So any question at this point?
No, sir.
Okay. So now we'll discuss mathematically. This is qualitatively. So now what you have to understand, what is the depth of this depletion width, what is the potential, built-in potential, what is the electric field. Okay. So all these things if you understand, right, you can use these equations and you can go to the non-equilibrium case. So we have to understand at equilibrium, what is the electric field generated, what is the built-in potential, what is the depletion width. It depends upon what. Okay. So all these things if you understand, right, then using this you can go to the non-equilibrium case and you can calculate the current. Okay.
Okay.
Yeah. Any doubt now?
No.
Okay. So let me go to my whiteboard. Okay. Okay. So equilibrium analysis of junction. Okay. So
Okay.
we know at equilibrium, right? If I take a PN junction, take a PN junction, right? So near the depletion width, we have a spacer region. Okay. This is nothing but my this is P. This is my P side. This is my N side. Okay. And this is called WP. This is called WM. Okay. This is my junction. Okay. And if I want to draw, right? Okay. If I want to draw the concentration due to holes. Okay. So in P side, right, the hole concentration is very, very high. I don't know.
Right.
This is called PP0. Right. Similarly, in N side, the electron concentration is very high. is called NN0. Clear?
Right.
Similarly, in N set, in N set, the hole concentration is very, very less. Right? So it will be very, very less.
Yes.
This is called holes in
PN.
G. Okay. So like in our example, it is around 10 power 16. Approximately, it is around 10 power 4 for CMQ. Clear?
Clear.
Okay. Power of 4. Okay. Similarly, if you see the electrons, right, it will be very less. Clear? It is around 10 power 4. It is NP0. So is it clear?
Yes, sir.
Okay. Very good. Okay. Now you see, because of the holes are diffused from N side to P side, creating a diffusion region, right? So what will happen? Right? The concentration cannot decrease abruptly, right? So it will decrease like linearly. Ready? If it will decrease abruptly, right? So there will be a, you know, the diffusion current is nothing but dp by dx will be infinite, right or not? Hello?
Yes, sir.
Yes. Similarly, in N side also, so between here NN0 will go to NP0 gradual manner. Okay? Okay?
Yes, sir.
Okay. So, see, this is 10 power of 16, this is 10 power of 4. Okay? So, in between it will go from 4 to 5, 6, 7, 8, 9, 10, 11, like that, it will go up to 10 power 16. Right? So, if you want to plot the same thing in this is in log scale, right? This is log scale. Right? If you want to plot in the linear scale, right? The linear scale, how it will be? If you see, okay. If you I'm putting the PP0, right? PP0, PP0. Okay. You see, 10 power 16. Okay. Then it will go to 10 power 14. 10 power 15, 14. Okay. So if you see, if you move little bit distance, right? 16 to 14 means 100 times less. Okay. So if you put in linear scale, it will be very, very less like this will come. Okay. Like it will behave like this. This is the whole concentration. Right? Similarly, if you want to plot the electron concentration here, it is 16 here. Okay. If you move little bit, right? 16 it will reduce 10, 100 times, 1000 times. So very, very far distance it will be very reducing like this. Right? So what it looks like near the junction, there is almost Keresa 0. Okay, but actually it is not 0. You see, it is going from linearly like it is going like 16, 14, 15 like that it is going. Okay, but if you see in linear scale, it looks like very, very less. Okay, that's why it's called depletion region. I don't know.
Right, sir.
Okay.
Yes, sir.
Yes. If you want to plot the charge density, right? Charge density. So this is my. So that's why I just draw this diagram to give you a feeling of the carriers are not zero in depletion region. Okay, they are very, very less compared to the neutral region. Okay.
Okay. Okay.
Now, if you suppose go to the
So previous case inside is slightly doped.
which one?
The previous case,
Which is
this one,
what?
this one.
Which one?
Is
No,
the
no, no.
inside is
No,
slightly doped.
No, both are similarly doped. Okay. So both are equally doped. I have assumed. See, 10 by 16, 10 by 16. I've taken.
Okay.
Okay. One more thing, when I have gone to IIT Kanpur for an interview, okay, they've asked me a question on this diagram. You understand how these diagrams are very important. Okay. So I got a question. I also did not know I'll get this question. Okay. I answered the question. They become very happy. But the question, they've since Sojit asked a question, right? That's why this question come to my mind. Okay. They have told that this is 10 power of 19 per cm3. This is 10 power of 17 per cm3. Okay.
Yes, sir.
Okay.
Then they told me to draw this diagram. Not this diagram. This is energy band diagram. Okay. So later I will show you how to get energy band diagram. They will recall me based on this question, right? They have asked me to calculate the energy band diagram. Okay. So that is then I'll tell you later. Okay. So in summary, what you got is okay. Near the junction we have the depletion region, right? See, depletion region. Okay. This is the N junction. Okay. Here depletion region. So here it looks like. So if you plot here it is positive charge, right? I am getting the bounded positive charge. Here I have bounded negative charge. Okay. What is the charge density? If I want to plot, so inside in N time, what is the density? Nothing but donuts, right or not?
Right.
I want to plot the charge density. Okay. In N side, nothing but ND. Right. This is ND for centimeter cube. Right or not?
Right.
And in P side, what is that? It is minus NA, right? For centimeter cube. Because in P side I am getting negative charges. The P side, all the bounded atoms are negatively charged. In N side, the bounded atoms are positively charged. Okay, that's why if you plot the charge density, okay, and this is here it is neutral, right? Because here there is no charge. Here I want to show you how I will show. Okay, here if you see, this is in neutral region, right? Okay, so in neutral region, right?
Right.
Yeah, in neutral region, the positive charge equal to negative charge. Could you see my screen?
Yes.
So only in the depletion region, I have net positive charge. Okay, in the neutral region, all the positive charge is cancelled by electrons. Okay, the number of positive charge is equal to number of electrons that is donated. Similarly, in the P side, the number of negative charge is equal to number of volts that is donated. Right. So in neutral region, there is no net charge. Okay.
Okay.
So I have net charge only in the depletion region. Clear, Sujit and Sri?
Clear.
Clear. So since you have a
But
charge,
sir, but for like for inside in the depletion region, there is some minority carrier also there, na?
where
For holes.
they are very
Assuming
small, right? They are very small. Hey, we are talking about 10 to the power of 4. You see, we are talking about 10 to the power of 4 number of minority carrier. Okay,
10 to the 4,
so
yes, sir.
here
Yes.
this is 10 to 16, 16 to 14, 15, 16. It will be 10 by 10 something, 10 by 10 or 10 by 9 like that. Okay, so we have 10 to the power of 16 number of ND per centimeter cube. So where you may have minority carrier of 10 to the power of 10, order of 7, 10 or 9. How many difference?
Okay. Almost, yes, 10 is to 4, yes, sir.
6
10
order of 7
times.
order magnitude difference is there. Clear?
Yes, sir, yes.
Yes. So like see, if I write net charge, suppose you tell, so if I write 10 to the power of 16 plus 10 to the power of 9, so will be how much equal to it will be? 16 only, na?
Almost 10 is to 16, yes, sir.
Clear? Very clearly it's 16 only, right?
Yes, sir.
Okay. So in the in this region I got net positive charge and negative charge. Okay, then I have to get the electric field, right?
Right, sir.
If I want to draw the electric field, okay, electric field, we know electric field is like this, right or not?
Right, sir.
And we will
Yes,
know
sir, direction.
the electric field is 0 in the neutral region, and here also the electric field is 0. Clear?
Hmm.
Clear. So inside this inside, what is the electric field? We know d by dx. Sorry, you were not there. I have explained this one. It's equal to charge density divided by epsilon. This is what you call Gauss law.
Yes, sir, Poisson's law equation.
This is called this is called I think Gauss law.
Gauss law, yes.
Okay. So I have explained so before you come there. See? I will show you. Yeah. So what Gauss law is telling?
Okay, sir.
The
will
net
check.
increase in electric field, okay, depend upon the whatever charge included in the volume. There is a electric field entering, electric field leaving. Whatever increased D depend upon the total charge density inside the volume. From there we got the Gauss law. Okay.
Yes, sir, dv by dx. Yes.
Yes. D by dx Q and D by epsilon. Okay. Here in the inside, what
Right.
will in P side what will be? D by dx is equal to minus Q Na by epsilon. Right. So we know the electric field is 0 in this region. Electric field is 0 in neutral region, right? And in inside in this region, in this point, at this from 0 to I can say double n. Okay, this is double n. Okay, this double n. This is minus double p. I can write like this. Okay, 0 to double n. It is having a slope positive. D by dx is equal to positive. Okay, then how to write? It should be like this. Okay, d by dx is positive. D will be equal to this into some x or something, right? It is linear. So can I draw like this? Because if you do d by dx, it is positive. This is the only way, right? After this, it is 0. Okay.
Yes, sir.
Similarly, here d by dx is negative, so it should be like this. And the electric field is continuous, so it should be made at this point. Okay, this is the electric field inside the what you call represent region. Okay, electric field is linear. Clear? Because
So
d by
what
dx is
thing actually? Yes.
it's
So what thing actually ensures that these 2 points will, cutting actually at x equal to 0?
because the electric field should be continuous, right? Continuous. Electric field is continuous. Okay, there cannot be a discontinuous. See, we have a built-in potential, right? So if there is the derivative of electric field, sorry,
Yes.
I'm telling the electric field is continuous. Okay, there cannot be discontinuous in the electric field because you see
Yes.
there is positive. So and here the number of positive charge is equal to number of negative charge in the P side.
Yes.
Okay, that tells me that electric field in this side should be continuous only when if both are same meeting at this point. Clear?
Okay. Means charge equality for that you can
Charge
say.
equality will hold. Okay, and now and since you're asking question, I'll prove you also charge equality will be there. Okay, the number of charges in this region equal to number of charges in this region because you see the very beginning point I have discussed, right? There is electric field generated, right? Here you see there is electric field. Okay, so whenever we see a one positive charge and one negative charge, there will be electric field. So the number of field lines will be equal to number of charges, right? So the number of electric field lines will be depend upon the number of charges, right? And it starts from positive charge, it ends negative charge, right? Electric field always pointing from positive, start from positive charge and end negative charge or not?
Yes, sir.
Yes. So the total number of positive charge in this volume will be equal to the total number of negative charge in this volume. Clear?
So that sometime it is also happen na that WP may be greater than WN or vice versa.
That will happen. That will happen.
Yes.
So see, WP definitely. What is the total number of charges in the WC? So if I want to see what is the charge in double N side, okay, it will be equal to, okay, the charge density is nothing but ND is nothing but what? Per unit volume per centimeter cube. Okay, Q
Yes, sir.
into per centimeter cube into the area. Area is like this. Suppose take a unit area. Okay, into distance.
Hmm.
This is double N.
W.
Double N.
Yes, sir.
Okay, this here is how much area? How much is the third charge? It will be equal to Q Na into area into WP.
W.
Okay, so if
Sir.
Na is more, then WP should be less because this should be equal to Q ND into double N. Okay, they both should be equal. So if Na is more, then WP have to be less to make it equal, right?
Okay.
Okay.
Means
If
okay.
ND
Yes,
is
sir.
more, ND is more, then definitely double N should be less. So that Na and WP is equal to ND into double N. Okay, whichever concentration is more, there I need less distance. So see,
Yes, sir.
this is more, right? Na is very more. I need only to discover only to very less WP to get ND into double N. Right or not?
Okay, sir.
So it's about net charge, not volume. See, Na is volume charge density, but for getting electric field, there should be net charge. I'm talking about net charge.
Yes, sir.
Okay, so double P not equal to double M. Whenever there is a difference in doping. Okay,
Yes, sir.
okay. So this is my electric field. Okay, so and you understand that, na? Electric field should be similar to this one.
Yes, sir. Yes, sir. Clear.
So any doubt is there in this point? No doubt, na? Okay. So
No,
now
sir. Clear.
I am claiming Na into Xn equal to, sorry, not N into Xn, Na into Xp equal to Nd into Xn. Right? Total negative charge in depletion region equal to total positive charge in depletion region. Okay. Total negative charge here equal to total positive charge in the N side. Okay. And this is my,
Yes, sir.
this point is my E maximum. E maximum. Okay. And we know integration of electric field is nothing but what? Potential. Right. So if I want to find out the potential, built-in potential, right, I have to integrate the electric field. Right or not?
Yes, sir.
Huh?
Yes, sir.
Yes. Okay. Good. So first, so I just given you a qualitative manner. Okay. Let's discuss quantitatively how it come. So we know. So now my main aim is to calculate the double N, double P, electric field and built-in potential. Okay, in the equilibrium. Okay. So first thing is we know current was due to hole equal to 0 because it is in equilibrium. I don't know.
Right.
Right. Equal to minus Q into dP into dP by dx. So is it?
Yes, sir.
You were not attended this transport chapter, na?
Transport equation.
Transport chapter. You did not attend the class, na?
No, sir. No, sir. My net issue was there.
Okay. So have you gone through the recording?
No, sir. Not yet. I have not checked yet, actually.
Okay. So there you can see this is a transport equation we have derived very clearly for holes and electrons. Okay. The
Okay,
diffusion,
sir.
this is drip. These two things we have derived from basic equation. Okay.
Okay, sir.
Okay. So now if I want to write the electric field, simply electric field equal to, okay, Q get cancel, okay, dP by mu P into 1 by P into by dx. Okay. So dP by mu P is equal to what? Theory?
KT by Q.
Yeah,
No.
VT, thermal voltage. This is called Einstein relationship. Okay. This also we have derived. Okay. Yes. Okay. This is my electric field. Okay. So if I want to know the potential, right, what I have to do? integration of minus electric field dx equal to potential, right or not?
Right.
So it from P side to N side. Okay. So if I do this integration of Vt into 1 by P dP, right? This is integration you have to do. Okay. Minus what will you get? Vt ln P. Clear?
Clear.
Okay. So will be equal to from P side to N side. Okay. So equal to minus Vt ln P from P side to N side. Okay. Equal to minus Vt ln. What is the concentration of holes in N side? Equal to Pn0 divided by
NP0.
Ep0. Clear?
NP0. Okay, yeah.
Okay.
Yes, sir.
So we'll get Vt ln Ep0 by Pn0. Okay. So we got the potential equal to Vt ln Ep0 by Pn0. Okay. This is the pole concentration in PTS semiconductor. This is the pole concentration in N side. Clear?
Clear.
Yes,
Clear.
sir.
So this is my built-in this is my potential. Okay. Inside the depression field. Okay. So if you see Vt ln, what is the concentration of hole in P side is equal to Na, right?
Right.
Right. Right or
Yes,
not?
sir.
What is
Yes,
the
sir.
concentration of holes in the N side?
N square by ND.
Na square by Nd. Okay. So here what I got? Vt ln Na Nd by Na square. Na square is equal to your V built-in potential. Okay.
Clear.
So this built-in potential depend upon what? Doping and also the intrinsic concentration. Fine.
Fine.
So this equation is generic. Okay, this equation is generic. Okay, suppose there is two places. Okay, concentration is P1 by P2. Okay? Then you can directly suppose concentration difference between 2 points P1 and P2 will be directly you can put Vt ln P1 by P2. Okay, suppose there are two places, but the concentration difference is P1 and P2. You can put this equation, generic equation. I don't know.
Right.
Yeah. You can also suppose there are two region where concentration is N1 and N2. You can put the built-in potential equal to Vt ln N1 by N2. Okay. So you see, this is the way you have to derive. Okay. Just if you remember NAND by NI square in 2022 get 2022 or 21, 21 get. Okay. Get 2021. 21. Question came like this. Then nobody would answer. Also, in many of the I could see coaching center also did not give the correct answer because you have to know the source, how they derived. Getting main thing, this is the source. In the
Exactly, sir.
equilibrium, I got the electric field. Integrating electric field, I got the potential.
Clear.
Okay. So since this thing is not understood properly, then question came like this, not like straightforward. They won't give you NA, ND, put NI, directly put the answer and get the put the formula, get the answer. Okay. So you should be ready for if it need to derive, you have to derive. On this concept, the question is coming in the 2021 only, 2 marks. This is the objective. So you have studied so hard. We have mugged up hundreds of formula, but the get is not like that. You have to mug up and vomit in the exam. Okay. Even
So one question has also come for the same VY expression. How much is a function of T actually, the temperature basis? Is a strong
Ah.
function of temperature.
Yeah, temperature, na, NS square different temperature, result different temperature.
KT by Q.
Means
KT
if
by
we
Q,
increase that, is VVI increasing?
VBI versus temperature. Okay. A strong function of temperature. Yes, temperature. Yeah. You can show that na BC VBI is NS square depend upon exponential temperature, right? Exponential temperature.
Yes, sir.
Okay. Then you have to see how the building potential depend upon temperature. So VT is directly proportional to temperature. VT ln. Suppose Na and D suppose constant K. Okay. NS square is from constant K2 into exponential of minus Eg by 2 KT. Okay. Equal
Yes,
to
sir.
15 ln A1 by KT plus go Eg by 2 KT. Clear?
So in K2 part is also one T term is there, na?
Where? No.
In K2
Yes.
portion.
Yeah. So T power 3 by 2.
Yes, sir. Yes.
3 by 2. Okay. So it's a complex function now.
Yes, sir.
Okay. Pt ln A1 by A2 into 3 by 2 into exponential of Eg by KT, not 2 KT. KT. Right? By KT. Clear?
Na square, that means
Uh,
the root get cancelled, right, sir?
Which
Or
option?
actually in denominator it's Ni square.
No, that's why I put 2 KT instead of 2 KT, I put KT only. Na?
Okay.
Okay, this will be 3.
NC, yeah, yes.
Yeah, this will be 3. Okay. This will be 3. Right.
T cube, yes, sir.
Okay. See. Okay. Fine. So T power minus 3. So T power minus 3. So what I'll get? Minus 3 ln T. Okay. So what I'll get? A will get ln okay. What I'll get? Minus K1 by K2 to 3 ln T. Right? Clear? Plus
Yes.
Eg by KT. Clear, Surajit, now?
Yes, sir.
Yes. Now you have to see this is actually KT by Q. This is multiplying. This is not like that. Okay. KT. Okay, this is multiplied, right? This is multiplied, na? Okay. So
Yes, sir.
this T will get cancelled. Clear? This is KT by Q, na? This is KT by Q. This T will get cancelled.
Yes, sir.
Yes. So now what will be there? This T will come here. T ln T. Clear?
Clear.
So now it should, what is it telling? It should decrease with temperature, na? This is minus, na? Right? From this expression, it looks like decreasing with temperature, na?
Yes.
Fine, Surajit?
Yes, sir. Yes.
Okay. See, that's what I'm telling. You should not expect ki everything will be covered in the exam. What is asking? See, and I'm telling you, whatever we are teaching, definitely nothing will come in the exam. But what we are giving you is a way to analyze a question if you get a new question. Okay. You should be ready to analyze the question. And don't expect ki we solve some questions and we solve some formulas and that will only come in the exam. It is just
Yes, sir.
giving you a way to analyze a concept. Okay.
Yes. But sir, in option it is there increase with increase in temperature. One option is that. Another option is increase in the doping levels of the two sides.
Doping level when it will increase in the directly proportional, right? There's no doubt in that.
Yes, this one is correct. But third one is given in answer is also correct. Increase in temperature. It is given. This
Temperature.
should be wrong.
So then otherwise you go to the home, you do solve like this, you can know whether you have done some mistake or not.
Yes, sir. Yes, sir.
Okay. I'm just giving you a way how to solve the question.
Okay, sir.
Okay.
Okay, sir. I will check it.
Okay. So now, so thing is ki, if you suppose they will give you some, so this one more thing. So yeah, in get 2021, see theory, what happened, in 2021, they have given a profile of the doping. Okay.
Okay.
It's I think they're given a semiconductor. Okay. Then profile is like this, something. This is my whole concentration profile. Okay. Then they calculate, asked us calculate the built-in electric field of the semiconductor. Okay. You want to calculate the electric field. The question I will see, you can go through in this IGC classes also. I have solved the question. You put just a solution of GATE 2021 ADC. Okay. There they have solved. I solved this question. Okay. There we have to use exactly this formula to get this answer. How to get the electric field. Okay. Here you can easily, if you know basic, you can easily calculate the electric field.
Okay.
Okay. So both of you go to the GATE 2001, 2021. Okay, by EGC, which I solved all this paper. Okay.
Okay.
Okay, sir.
Yeah, you will get the idea of how question will come from the class. So if I would have taken the class, definitely I would have solved the question, solved this like this only. And definitely, if somebody understood this question, understood this concept, then easily they could have answered the question.
Sure.
But if you finally remember what is electric field, what is between potential, so I also could have completed this diode class in only one class. Maybe if you give me 1 hour, I'll complete the course. But I'll just give you a formula. VBI you like BT ln NM N by N square. Electric field you like this. So if I give one giving formula, like when I attend the classes for coaching, they are given the formula like this. Okay. So there
Yes,
you
sir.
don't have any intuition.
Yes.
Fine.
Very much.
Hello.
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
So yeah. So see, I'm just telling you after class you go through this content solution. Okay. You will understand how the question came from this concept. Straight to marks.
Okay, sir.
Okay. And when students will start studying, right? They'll understand okay, hey, who will do this derivation? No need. We will just remember the final formula. Okay. And this attitude definitely not give you a good rank.
Yes, sir, actually.
Yeah. I tell you,
I am
even
weak in
yeah.
weak in memorizing the final formula, sir, always. I cannot do that.
What? Yeah, if you memorize in a CPC, suppose in signal system, there are hundreds of formulas. Okay. So if you take dx by dt, what is the Fourier transform? If you do x by at, what is the Fourier transform? If you do the integration of x of t, what is the Fourier transform? Okay. Similarly, Laplace transform, Z transform. Hundreds of things are there. Then if you keep on remembering dx by dt equals j omega into x omega, and at x of t is equal to x of 1 by a, x of omega by a. If you keep on remembering hundreds of formula, okay, your mind will be very jam and you will be not in a good mood of mind to attempt the exam. Okay, if you would have know, okay, how to suppose if I put x of 80, what is the Fourier transform? Equal to 1 by a x of omega by a. Okay, then somebody will just remember. If somebody would have derived it, how it have come. Okay, then there is no burden to the mind. You go to the exam with free mind because you know how to derive. You can easily derive it quickly. Also, if you derive it, it is easy to remember. Okay, so the derivation is, I'm not telling you don't remember anything, but if you remember after deriving, then this will be imprinted in your mind how it would have come because you've taken 80 is equal to lambda. Okay, from there you got this equation. So it will be very easy to remember and very easy to reproduce in the exam if you forget also. Clear?
Exactly.
Similarly, Laplace transform, Z transform, similarly, QC control system. Okay, raise time, fall time, settling time. Okay, what is this? All things. Suppose raise time. If I ask you, okay, what is TR? Okay, pi minus theta y omega d. Something is coming, right? So what is the
Yes, sir.
overshoot? e to the power of minus some delta square by something 1 minus root of delta square, okay, minus 1. So at least once you derive all these things, right? Derive how it would have come. Don't remember like just simple formulas. Okay,
Clear.
Yes, sir.
because
And
if
this
you
year
remember, right?
also one good question is coming from EDC that is totally based on derivation actually, sir.
Yeah. So that since you raise this point, I will show you. Okay, this question nobody will solve, right? I have solved. I will show you. Just give me 1 minute. I will
Yes.
show you. Nobody have derived this question.
Yes, sir. I have checked it.
Yeah, but I'll show you how I derived this question. Even though I am taking some time in the class, okay, we'll tell you to how if you study from basic how it is really helpful. Okay, just to prove you. So he is my teacher in S Academy, but he become friend of me. So he always give me some questions which need to solve. Okay.
Okay.
How to know the? I will show you. How to go to the media and links. Okay. That question is on BJT, right? We are talking about.
One said generation and recombination rate based that question.
Yeah. Okay. Anyway, I will. Tomorrow I will show you maybe. Otherwise, okay.
Okay, sir. No issue.
Let me because it is taking some time to download. Okay. Tomorrow I will show you. So
Okay, sir.
the question in recommendation I remember is given one profile, right? Given one profile
Yes, sir. Yes.
like this,
Generation rate and recombination
like
rate.
this, right? Profile. Then it is asking the some
Yes,
current
sir.
or something. It is
Like
asking. Okay.
current,
Right
I
now?
guess. Current at exactly 3L, I guess.
Yeah.
I just
Yes.
totally blank out how to approach
This
that
one,
kind of
this one,
that
right?
totally
This
lost.
question. This is, I think, from BJT or something. This question is from BJT or something. See, this is looping in base or something they are asking. Okay.
Yes, sir.
This-
From continuity equation, I think we have to derive that.
Yeah, exactly. If you don't know the continuity equation, right? Here you see many coaching center, right? They don't even teach continuity equation. Can you remember?
Yes, sir.
Okay. So you see, we have taken how many classes to almost one classes we have taken the continuity equation.
Yes,
Okay.
sir.
Continuity equation. See, we have taken almost one
Yes,
class.
sir.
Now
This
we have
one
derived
is
the
very
continuity equation, not like just written the equation. Okay. We have derived from the basic how the continuity equation come. Then even if you forget, right, you can easily
yes, sir.
get it the answer, right? Right or not theory.
Sure, sir.
Exactly, sir.
Yeah. So this continuity equation we have derived.
Exactly, two questions coming in this year actually based on the same continuity equation.
See, I'm telling
One
you,
question is I think everyone know the formula del n minus t by tau n. That question is everyone solved, but this question everyone trapped because not
what I told you in the
knowing
beginning,
the solution.
if you want a differentiated rank, so you should do something differently. Okay. If you solve some question
Yes,
which
sir.
is solved by others, then how you get a rank? You know, rank is just relative, right? You have
Exactly,
to
sir.
you have to solve something which is really intuitive and conceptual, apart from solving the normal questions. Then only you will get the rank, good rank. Remember this one, and that will be coming only if you read the things from concept, from the basic. Okay, like I showed you, x of 80 should not be equal to 1 by x of double by a. You should not remember this one at all. You should derive once at least.
Yes, sir.
Okay. Similarly, built-in electric field, definitely you will remember it finally. But thing is, you should know how it would have come. Okay.
Yes, sir.
Yeah. So let me cover. Otherwise, we will be back for this. Okay. So understand that now in general situation, right, we can easily calculate the built-in electric field if there is a concentration difference will be there. Okay. Now we'll come back to we know this is my area under the electric field, right? Area under the electric field will give you a potential. Okay. Right or not?
Yes, sir.
So area under electric field. Okay, so we know is equal to the potential. Okay, so we know the area under electric field is nothing but how much here you see. So this is em. Okay, so what is the area? So this is the diffusion width hd. What is the area of this? Area of this is equal to
half xd into
half into em into hd equal to I0, right? And we know simplifies I0 is equal to half em. hd is nothing but action n side plus action p side. Clear?
clear.
Clear. So today
Yes.
at least we'll try to complete the equilibrium. Okay. So also we know one thing, because of the charge equality. Okay, we know xn into nd equal to xp into na. Right. So we'll put in this above equation. What will you get? So I0 equal to half em. Okay. We'll get nd by na plus 1 into xn. Clear? I just put xp is equal to nd by na into xn. Okay.
Yes, sir.
Yes. Okay. This is thing you got. Then I want to calculate my aim is to calculate the depletion width. Okay. So how to calculate depletion width? You have to get xn. Okay. Then one more thing we know from the Gauss law. What is the Gauss law? Gauss law told that d by dx is equal to q nd by epsilon in n side. I don't know.
Mhm. Yes, sir.
Epsilon. Okay. What is d by dx? Em by xn na? It will be equal to Em by xn is nothing but d by dx na? But this Em by xn is nothing but d by dx. Huh?
Yes, slope.
Slope of that one. Okay. So I can put like that. Em by xn is equal to q nd by epsilon. Right? So from here you calculate what is xn. Xn is nothing but xn is equal to epsilon into Em by q nd. Right? You put this one here. Okay. Is equal to half Em what is xn? Xn is equal to epsilon q nd. Clear? Equal to I naught. Is it right?
Clear.
What is half em square into epsilon by q and d, right, equal to 70. So is equal to half em square into epsilon divided by q and d half into em square by q and d q and d nd by na plus 1 equal to psi 0. Fine.
Fine.
Okay. So
Yes, sir.
what is em now? Em is equal to okay, 2q psi 0 divided by epsilon. Okay, nd will go to this side. So nd will get cancel. 1 by na plus 1 by nd. Okay, into 1 by na 1 by nd whatever. Clear? See epsilon what happened? 2q psi 0, 2q psi 0. nd have gone inside. nd get cancel. 1 by na 1 by nd by epsilon. Clear?
Clear.
Okay. So this is my maximum electric field. Okay. So now I'll put this equation. I know half maximum electric field into XD is equal to I naught, right? If I put this here, EM, and I'll get the XD, na?
Yes, sir.
Right or not?
Yes, sir. Yes, sir.
So you put this one half into root over of 2Q I0 by epsilon 1 by Na plus 1 by Nd, okay, into XD equal to I0. Okay, from here, if you solve this, we will get XD. Okay, what is XD? XD is equal to root over of 2 epsilon
Epsilon sin
I0 by Q into 1 by Na plus 1 by Nd. Okay. This is the replacement width. Okay, replacement width depend upon what? Na, Nd, and
Yes, sir.
building potential. Okay,
Great.
great. So if you, so this is nothing but replacement width, total replacement width. Okay, so if I want to ask you to calculate the replacement width in N side or P side, so it's how to do. So we know Xn plus Xp is equal to Xd is equal to root over of 2 epsilon Vbi or psi 0 by 2 epsilon Vbi by Q
yes, sir.
1 by Na plus 1 by Nd. Okay, suppose I want either Na, either Xn or Xp. How to calculate? Please tell me. Cherry, you can tell me.
So
If I
for
want
that
to
equation,
either Xn,
Na into XP,
what?
Na into XP equal to Nd into
Perfect. What is Xp?
Xn.
Xp is equal to what? Xp is equal to Nd by Na into Xn. I don't know. Is equal to this one. So
Yes,
it
sir.
will be, what is this? It will be Na plus Nd divided by Na, Na plus Nd divided by Na into Xn is equal to this one. So Xn is equal to, you have to Na by Na plus Nd into root over of 2 epsilon 0 by Q Na plus Nd by Na Nd. Right?
Yes, sir.
You just take inside how much it will be. Okay. Na plus Nd is a whole square, so it is square, so it will get cancelled. 2 epsilon I0 by Q. So Na plus Nd whole square, this is N, so it will be below Na plus Nd. I don't know. So Na will go square, so it will be Na by Nd. Right? This is the representation width towards N region. Clear?
Okay. Yes.
I don't know.
Yes, sir.
If I want XP, what will be? Similarly,
Na, one second.
1 by Na plus Nd into Nd by Na.
Okay, it's cancelled.
Okay.
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. So these are the long formulas. You just don't mug up blindly. Okay.
Sure, sure.
But just to have an understanding that represent width depend upon the doping. Okay. High the doping, low the represent width. Because you know, to generate the same amount of electric field, I need to uncover only few amount of distance. Okay. Because the doping is more. When doping is more, if I cover little bit distance also, I'll get more number of charges. I don't know.
Yes, sir.
Clear? So that's why if I go to higher and higher doping, and represent width should be less, right? Because in a smaller distance, I will see per unit volume more number of charges. So I'll generate the same amount of electric field to oppose the diffusion force, even if I uncover a smaller distance. Fine.
Right.
Fine. Okay.
Yes, sir.
So this is my equilibrium picture. See, in equilibrium, what you understood? I understood the depletion width N side, P side. I understand what is the maximum electric field. Okay, so then I understood what is built-in electric field. Okay, see, suppose in some exam they will ask you what is maximum electric field. Okay? They'll give you doping and all things. Then if you can you remember this formula and go, right? It's a 2 mark question, right? Simply one step, right? One step only. Half so half AM and
EM
XD equal to psi 0. Okay, so from here, suppose you remember only one formula. Suppose you remember only one formula. Okay, directly put that formula here. Just simply equal to psi EM is equal to 2 into psi 0 by XD. Clear? So you do not mock up only one formula for EM, right? Because
Yes, sir.
you know, suppose if you know only depletion width, from depletion width you can easily calculate the maximum electric field, right? Using this equation. I don't know. So don't remember separate formula for HD, separate formula for EM. Okay, but your mind will be very much clumsy. Just remember only one formula for HD. From HD you can easily calculate EM. Clear?
exactly.
Okay. See, because both EM and HD will depend upon similar factors, Na and D. EM also depend upon Na and D only. So only one formula I need to remember. Okay.
Okay.
Okay. So this is one more thing. So I think 10 minutes is there. I can cover the Venn diagram of this in equilibrium. So I'll cover next class. Venn diagram of the semiconductor. So I want to cover the Venn diagram. Okay. Then we will continue with the calculating how. Suppose if you go to non-equilibrium, suppose I apply external bias, forward bias or reverse bias. Okay. How the current flow. If you cover that much nicely, then almost we'll cover the diode chapter.
Okay. Okay.
So
So
you want
means if we increase the depletion width, so in means which thing we have to make the constant, like the built-in potential or peak electric field? Means both are very enough here.
what is your question?
Means if we increase the depletion width from its nominal value, in that case, what thing we have to make the
If you
constant,
want to
like
increase
peak
the
electric field or the
depletion width,
yes sir.
you want to increase the
In
depletion
that
width, na?
case, yes sir, depletion
So
width.
simply
And in that case,
you have to decrease the doping. That's all. You decrease the doping. So if you increase the doping, it will decrease.
okay. So in that case, sir, what thing will make the constant? Means VVI will remain same or peak will remain
VI also depend upon Na and NS. Why VI will remain same? If you increase doping, everything will change. This will change. VI
okay.
will change. Electric will change.
Yes, VVI
Nobody is
change.
nobody is forcing me to make a constant anything, right? Okay.
No, sir,
If you change,
how
if you increase doping,
that
okay.
particular thing VVI is yes, sir.
Pardon me. If you increase doping, right, Na and ND, right? So the depletion will be smaller. Phi 0 also will be different because it's Na and D by Na square. Okay. Similarly, the electric field also will be different because both are different. So all the things will change if you change the doping.
Okay. So I'm thinking that the area under the curve, or area under the electric field give the potential. So
Area under
in
the
that
field
case,
will give
that
the
I was
potential, but the thing is, it depends again upon the doping, right? So thing is, suppose okay, suppose I have a device one, okay, 30% base is like this, okay. If I want to plot the electric field, it will be like this, okay. Suppose I have another thing, I don't know how it will be. It will be sorry. Suppose I have another device, really like this, okay. In small region, right? I have to maybe I have might be like this, okay. The
okay.
built-in potential also will be changing. The electric field will change. Also, the depletion base will change. Three things will change. Nothing is constant.
Okay. Yes, means yeah, when doping is changed, then yeah, everything is going to change. Yes.
Everything is
The
going to change.
number of carriers are going to change. So depending on that, everything will surely affect the exam.
Yeah. So what are things
Okay.
remaining? Okay. we have to know the energy band diagram, which I face a question in interview, I told you, right?
Yes, sir.
Energy band diagram. Then you have to calculate the forward bias current. What will happen in reverse bias? Okay. In reverse bias, we'll get something called depreciation capacitance. Okay. These are the main things that is remaining. Okay. Another remaining is called breakdown. How a diode will break down. Okay. But is there in the syllabus or not? I don't know. We'll see. Okay. If it is there, we will cover this. Okay. These things is remaining. Okay. So looks like we have to cover. We'll take 1-2 classes to cover these things. Okay. Then we can go to the BJT. BJT you can, if you see, if you understand diode, right? BJT can be covered quickly. Okay.
Yes, sir.
Okay. So I think we will take freshly these chapters, energy band diagram. Then next class we will try to cover these two things. Also, hopefully we will try to cover up this diode next class. Okay. And I am very hopeful. Up to diode, if understood very well, right? We are going to answer almost all the question of EDC. EDC means they will ask mostly up to diode. Okay. After BJT and MOSFET, right? That will be coming from analog circuits, most probably.
Yes.
So, but what thing is ki BJT is very important. So we'll cover try to cover at least in 1 hour or 2 hours the basic things of BJT. Okay. So
Yes.
maybe next class we will take
See,
diode.
Bharat actually.
Huh.
Yes. Say, Bharat exam, the question pattern is similar for the gate pattern. I mean, little different, or more than that.
Bark is not taking from gate now.
This is they are conducting separate exam actually.
It will be, see, it will be similar to gate. And you remember the interview of bark for bark compared to all other government exam is very good and very different and very conceptual and really good exam. If you are understanding things from the depth, then only you can answer the question. Okay. So bark interview
Yes, sir.
better than any other exam interview like ISRO or DRDO or BEL. Okay. Whichever PSU, NTPC, whichever interview you go, right? Bark interview is good one.
Okay.
Okay. Because I have faced this interview once.
Okay.
So we'll ask you 3 to 4 subjects or 5 subjects of your favorite. Okay. So from each subject they'll ask you question.
Okay.
Okay. So we'll try to bind up this diode part next class. Okay. So one more class we will take for BJT. Fine.
Okay.
Okay. Okay. So whatever we have covered today is very clear. Or any doubt is there today?
Yes.
Clear, na?
Yes, sir. Yes, sir. Clear.
Yeah. Okay. Okay, guys. Then good night. See you in the next class. Okay.
Thank you, sir. Good night, sir.
Okay. Thank you.
Yes, sir.